Just before I get into this talk, I was, before Dr. Kramer came in, I was given an introduction of where I was from, and some of the things we might talk about a little bit later that we had actually started talking about before the talk. But today, really, what I want to focus on is some research that has been completed over the last 3 years at Kirtland Air Force Base in New Mexico. And we had a need to determine a better way to scale what's called a DPAL, a diode pump alkali laser, the power on that without destroying the gain beam, if you're familiar with lasers. And this effort was designed to make that possible for a highly efficient next generation laser system. So in this talk, I'll go through an introduction, and then I'll go through our research approach, what's the current state of the art for diode pump alkali lasers, a functional block diagram of a DPAL, a rubidium DPAL. We go into background and theory, rubidium-induced glass, and DPAL failure mechanisms. Give a model for rubidium absorption. It's actually a pretty lengthy list. I hope we can get through all of this. And selection criteria for optical thin films and materials, and selected thin films for DPAL optical windows. At this point, I think I'll need my laser pointer here. So this is general. We have several experiments related to the effects of rubidium vapor on bulk glasses, which includes a DPAL emulator, experimental setup, measuring the laser power transmission through the exposed material, optical window damage and surface roughness. And we also did some experiments on deposition of thin film aluminum oxide by polymer-assisted deposition. And we'll take a look at the coding process and some characterization completed on that film. And then we looked at the natural oxidation of air for a flash deposit aluminum, physical vapor deposition, and oxidation of thin film aluminum, and introducing the witness sample into the gain cell emulator, and getting a little bit of the theory of optical filter design, application of the Fresnel equation, and what constitutes optical quality of thin film. So this is a pretty long outline. So essentially what we're trying to do is to get to a design of an optical thin film, what's called a Fabry-Perot resonator, which essentially a Fabry-Perot filter, which will be placed on the gain medium optical windows for high transmission. And we've created here a simulation tool by which we can change the composition of the thin film, different materials, in order to be able to achieve our objective. We discussed the Gibbs free energy, enthalpy, electronegativity, the potential thin film reactions with rubidium. We get into the mechanisms of laser damage and operative damage phenomena, and effects of rubidium inclusion in thin film, self-focusing, electron avalanche, electric field contribution of a high power laser, electrical mobility, Einstein's contribution, Stokes-Einstein relations, defect classification, and so forth. And ultimately, we want to have an integrated solid optic which eliminates the need for a resonator portion and utilizes a highly reflective mirror on the back end of the film. So, having gone through that, essentially, what are we really trying to do? We have optical windows in a deep power gain cell that degrade in the presence of rubidium vapor. So our thesis or thought is that the top layer, robust, thin film, damage resistant, high optical laser transmission thin film is needed to reduce or to eliminate the degradation of the optical windows in the deep power gain cells. And further, a top layer protective optical thin film can be applied to the optical windows of a deep power as part of a Fabry-Perot optical filter to increase the laser energy throughput to close to 100% at the input pump and output laser wavelengths. And we do all this based on a fundamental understanding of the factors affecting diffusion and laser damage for selected thin film optical material. So what does it look like, a deep power gain cell? What you're looking at here is a Brewster angled gain cell, which essentially is actually a very small length. And what you see in there is a rubidium after it's been heated and cooled. And we'll go later into the atomic transitions of rubidium to make this happen. But essentially, what happens is we pump a diode laser into one end. It doesn't have to be a diode pump laser. It can be an indium YAG. But a DPAL is a diode pump alkali laser. But if you're doing an experimental setup, you are essentially just really trying to find a high energy laser that you can pump in, and whatever is most convenient you can use. So in this case, this is a 20 kilowatt laser, and the result was that the DPAL, it overheated. It produced, first of all, the DPAL itself contains rubidium with a 6-to-1 ratio with ethane or methane in this case. Sometimes we use helium as a buffer gas for, to deal with the atomic transitions, or just to make sure that the more hydrocarbon you end up using, the more trouble you run into in terms of the relaxation time of the process. So basically what you're looking at is soot. So you're looking at damage on the window of the gain cell, and these are the optical windows. So you come in at one end and go to the other. So in this case, we did some spectroscopy, Raman, and determined that this is the material found for micron resolution. These black deposits of what would be considered soot. We suspected it was soot, but then we confirmed the presence by actually, looking at the spectra and comparing it with known spectra for amorphous carbon with hydrogen present, and pretty much confirmed that 1600, the Raman shift, and was fairly confident that that was soot that had been produced by dissociation of the ethane. So, as far as laser pumping, we use for this particular experiment, one of the more important things is to determine the slope of the rubidium gain cell. The laser, when you're pumping, the PL, PN gives an efficiency factor. And if you're familiar with a electrically pumped laser, battery powered, versus a chemical laser like a fluorine iodine oxygen laser, what you have is a stark difference. One is highly chemical, has a lot of chemicals, requires supersonic flow in order to get the pumping of the gain medium. And then on the other hand, you have electrical pumping, which requires a huge amount of batteries in order to do it. So in this case, what you have is a hybrid laser. So this hybrid laser is a compromise between the two. It's a lot smaller. You can pump it with any known really low quality, non-gouging type laser, and you still get a hyperfine, really high power output from the laser. So what we're looking at is a neodymium YAG and a dye laser combination to produce 780 nanometer. If you're familiar with rubidium or alkali lasers, what you're looking at is it could be anything from sodium, it could be lithium, it could be potassium, it could be as high as francium, but of course francium is radioactive, so those really don't exist. So usually we stop like around cesium, and you can pump any of those. One of the best pumping lasers, and we use them in satellites and GPS systems, is the rubidium standard. So this is a setup which shows how we steer the laser into the gain medium. This is slow. As you can see, you're looking at on the second run. On the first run, we got over 80% efficiency. On the second run, we got over 90%. These lasers have been known to pump at up to 98% and could theoretically go much higher. This is a path. This just shows how the laser, how we've steered the beam into the resonator section. So this is the optical path of 780 nanometer wavelength laser. This is the resonator section. So what you're looking at, and you see a little bit later in the diagram, is an oven. So this is an oven configuration which exists around the gain cell. So the gain cell that you saw earlier is actually covered with this oven, which is electrically stimulated for heat up to 200 degrees Celsius. And so anyway, before we go any further, you may want to know earlier on what are the highlights of this research. And that's my pointer isn't